Hi there. Today we're looking at high-performance, large-scale image recognition without normalization by Andrew Brock, Soham Day, Samuel L. Smith, and Karen Simonian of DeepMind. This is otherwise known as NFNets, normalizer-free networks. So the point of this paper is to build networks, in this case specifically convolutional residual-style networks, that have no batch normalization built in, and we'll get to why during looking at this paper. But without the batch normalization, usually these networks are performing not as well or cannot scale to larger batch sizes. However, this paper right here builds networks that can scale to large batch sizes and are more efficient than previous state-of-the-art methods. So if you compare them to something like an efficient net, and I called it, you shouldn't call your model efficient net because a more efficient model is going to come around. So NFNet are now officially efficienter net, okay? As you can see right here, to reach the same accuracy as an efficient net B7, you need, I think they say they have an over 8.7x speed up if you look at the training latency, and that's going to be important while looking at these experiments in a second. And if you train for as long as the EfficientNet B7, you can reach a higher performance. This is ImageNet Top 1 accuracy, and this model is a new state-of-the-art without additional training data, and it is also a new state-of-the-art transfer learning, and it is the currently ranked number 2 behind a method that uses semi-supervised pre-training with extra data. So in the kind of global leaderboard, it's number 2, but it is number 1 in various categories. The ImageNet has now become, like speed running. There's glitchless, and the equivalent is like additional training data less, and so on. In any case, we'll go through the paper. We'll discuss what the tricks are to get the normalizer-free networks to work. I do have also a fair bit of, let's say, criticism against this paper right here, but in general, it's a pretty cool paper. The code is available. I'll, of course, link to the code. You can try it out yourselves, and that's, it's pretty cool that the code is available. All right. If you like content like this, as always, don't hesitate to share it out. Consider subscribing. Let's dive in. What's the problem with batch norm? Batch norm, as you might know, I've done a video on batch norm, but essentially what it says is that if you have a data point that goes through a network, it will experience various transformations as it goes down the layers. However, some of these transformations are quite unfortunate if you build the network a little bit in a wrong way. So what might happen is that your initial data distribution might be, in machine learning, it's good practice to center the data and around the mean and kind of, scale it to unit variance or something like this. But then as you progress through the layers, and especially if you have something like ReLU layers, they only extract the positive part of the signal. So with time, it can happen that the intermediate representation right here, for example, is, something like this. So it's very skewed, it's not centered, and so on. And the current methods we have in machine learning, they just work better if your data is sort of well-behaved, has a nice condition number, is centered, and so on. So what batch norm does is every layer, it comes in, it looks at the current batch of data, the current mini batch, and it centers and rescales it. So what it would do is it would transform this data by a simple standardization procedure into a well-behaved data set. Of course, remembering the transformation for a backprop and then feeding that data to the next layer. That's batch norm, and it has several disadvantages. So the disadvantages of batch norm, this paper identifies 3. Batch normalization has 3 significant practical disadvantages. First, it is a surprisingly expensive computational primitive which incurs memory overhead, okay? Which is, you need to compute these means and these scalings, and you need to remember them for the backprop. All right. Second of all, significantly increases the time required to evaluate the gradient in some networks. I mean, there is some backprop you have to do through all of this standardization. Second, it introduces a discrepancy between the behavior of the model during training and at inference time, which is also true because at inference time, you don't want this kind of batch dependence. You want to be able to feed a single data point and the result should always be the same, irrespective of the other data. And people usually do this so at training time, you simply calculate this mean shift right here and the scaling that you have to do. And what you would do is you'd have kind of a database, a special buffer where you save these things for every batch. And then at test time, you simply look at your buffer, you kind of build a moving average over your training data, and you'll simply use those shifts and variance. So you have a discrepancy between training data, which just looks at the current batch, and inference, which looks at your average over the last few batches. And third of all, and this introduces hidden hyperparameters that have to be tuned, which is kind of how fast the mean decays in your database. And third, most importantly, batch normalization breaks the independence between training examples in the mini batch. Okay, so it now matters which other examples are in the batch, and that has two consequences. So the first consequence is that batch size matters. So batch size matters in batch normalization. If you have a large batch, you can compute these means of the data. They are a much better approximation to the true mean of the current data set at this particular representation than a small batch. So if you just have 3 examples, the mean is going to be a very noisy approximation. Whereas if you have a large batch, it's a good approximation. So batch size matters for batch norm. And second of all, so distributed training becomes extremely cumbersome because if you do, for example, data parallelism, which means that here you have your batch of data, and we know for some applications that large batches are pretty favorable for training. They stabilize training. You can do larger step sizes and so on. So what people do is they split the batch. They shard one batch into, let's say, 3 different parts, and they have the network on 3 different machines. So the same network is on 3 different machines, and what you would like to do is you would like to forward propagate all of these batches through the network, this whole batch in 3 different shards through the network, and then backpropagate and sort of communicate the gradients around. But now imagine if you have a batch norm layer. So if you have a batch norm layer right here, it's going to be the same here, and it's going to be the same here. What you would have to do technically is you have to forward propagate the signal right here to the batch norm layer, and then you'd have to communicate these batch statistics between the batch norm layers, because otherwise you don't have the mean and the variance over your whole batch that you feed in, right? You can opt to not do this computation, but then again you run into the problem that usually the number of samples in the shard is fairly small and you have a bad approximation. So batch norm just kind of makes certain things complicated, right? And this interdependence of training data points is one of those things, and they call it the most important things. So they say this third property has a range of negative consequences. Practitioners have found that batch normalized networks are often difficult to replicate precisely on different hardware. Batch normalization, the cause of subtle implementation errors. Okay, well, yeah, especially during distributed training. And then it cannot be used for some tasks since the interaction between training examples in a batch enables the network to cheat certain loss functions. So this is, let's say you have a time series prediction, right? And in a time series prediction, so you have your time series and you want to make training samples of it. So what you usually do is you say, well, this is my input and this is my goal. And and this is my input, and this is my goal. So it's like language modeling if you do that. So you want to slice one sequence into many training samples. So you do like overlapping training samples. So like this is the input, and this is the goal. Now, imagine you have those two things in the same batch. Then technically, this training sample here could just kind of, by means of the batch statistic aggregation, information can actually flow, because this here technically is part of the input of one training data point, but it's the label for the other training data point. So there can be information leakage in that. So you shouldn't use batch norm or anything that connects the training samples to each other in these particular cases. It's kind of an edge case, and you can probably get around it by just having a big data set and shuffling a lot. But still, so they say they solve all of these things. Specifically, they say, we propose adaptive gradient clipping, which clips gradients based on their unit-wise ratio of gradient norms to parameter norms. And we demonstrate that AGC allows us to train normalizer-free networks with larger batch sizes and stronger data augmentations. So their method of circumventing batch norm, of building networks that don't have batch norm anymore, is going to be this adaptive gradient clipping. It's going to be in combination with earlier work from an earlier paper that they've done. But this paper introduces specifically the adaptive gradient clipping. You're going to see it's a pretty simple idea. It should be implementable in pretty much any network out there. And it has the potential to become kind of a staple component in deep learning, if it turns out to actually work as well as they say in the paper. They say, we design a family of normalizer-free ResNets called NFNets, which set the new state-of-the-art validation accuracies on ImageNet for a range of training latencies. Okay, so they repeat these things from what I said in the intro, and they also say achieve substantially higher validation accuracy than batch normalized networks when fine-tuning on ImageNet after pre-training. So they also have a good transfer accuracy. Now, my first problem with this is that the two things here are kind of not very related. So the gradient clipping is an actual, let's say, a contribution. It's a new method. They suggest it, they measure it, absolutely cool. But then they go around and they do like giant architecture searches for how could we replace the convnet block and so on to come up with these NF nets, which is also cool, but it is not clear to me that these two things are necessarily as connected as they make it to be. Of course, they would say, well, since it's normalizer free, we can build some, but I don't see why you couldn't just do like better architecture search for classic batch normed networks. So it seems like, and then you don't know where the gains actually come from, like whether or not you need the gradient clipping or whether the contribution here is actually to figure out a kind of a better ResNet architecture. You know, who knows? In any case, the structure of the paper is as follows. They first go, what does batch norm do? What does it do well? And then how can we replace all of the things that it does well by our own stuff and then not need batch norm anymore? So they identify 4 things. Batch normalization downscales the residual branch. So in a ResNet, you usually have an input, and then you put that through a series of layers to the output. But first, you add the input again. So you add the 2 and this. And this part is called the residual branch. It's kind of, so this is the identity function. I've done a video on ResNets if you want to learn more about that on residual networks. And batch norm will downscale the residual branch implicitly. And that just means that the signal strength is more in favor of this identity function, which is the entire point of ResNets, which makes training more stable. Second, batch normalization eliminates mean shift, and that's the thing we said before, that, for example, if you have ReLUs or something like this, they only retain the positive part of the signal, which leads down the network to quite a shift in the mean of the data, and batch norm eliminates that. Third, batch normalization has a regularizing effect by means of the batch statistics are noisy, which we said is a problem for inference, yes, but it is also has a regularizing effect during training. And lastly, batch normalization allows efficient large batch training. So it smoothens the loss landscape, and this increases the largest stable learning rate. Okay, so we want to get to a point where we get all these benefits but don't need batch norm anymore. So first they introduce their old paper, and their old paper, it's not that old, I think it is this one here. You can see it's also this year. It's an iClear paper, and there they built these normalizer-free ResNets, these NF ResNets, not to be confused with NF nets, which this paper introduces. Okay, so the normalizer-free ResNets already tried to build normalizer-free ResNets. They manage to build networks that train, but they don't beat the efficient net efficiency yet. What they do specifically is they just pay attention a lot to scaling. So they introduce, for example, these parameters alpha and beta, and what they do is essentially in every single block in the neural network, they try to very carefully predict how this block will change the variance of the data. And then they build constants here. So this is this alpha or is this beta? I think this is alpha goes after and beta goes before. They build constants alpha and beta. These are constants that are made particularly for the architecture. So if this is like a conv layer, they pay attention and they make these constants such that the variance kind of stays constant as you go down the network. So it's very much like people build deep learning frameworks where for every operation you have to define a gradient and then you can chain them together. Here, for every block, they carefully think about how it affects the variance of a signal, and then they design appropriate scalings to bring that variance back. And if you do that consistently, and it is quite hard, right? And they have to do a lot of things. For example, also kind of a variant of weight standardization and so on. But if you do this, then you can train quite large batch sizes. So normalizer-free ResNets match the test set accuracies achieved by batch-normalized pre-activation ResNets on ImageNet at batch size 124. They also significantly outperform their batch-normalized counterparts when the batch size is very small, but they perform worse than batch-normalized networks for large batch sizes. Crucially, they do not match the performance of state-of-the-art networks like efficient nets, and this paper is going to fix this. All right. The main way, or one way, the thing the paper introduces is this adaptive gradient clipping. Now, what is gradient clipping? So usually, right, you have a parameter. It sits here in the parameter space, and then you get a gradient, and you follow that gradient. You go like over here, down here, over here, down here during training. Now, sometimes you have a batch of data that just tells it to make a huge jump. And these huge jumps are often the cause for training instability. Because, for example, if you use SGD with momentum, that thing will get into your momentum term and just skew the training over here. It will screw with your atom buffers and even plain SGD. It's not really good if you take giant jumps. So gradient clipping simply says whenever a gradient of any parameter is larger than a size, let's say this size here, we'll simply clip it. We'll scale it, so that's the maximum length. So if it's a good gradient, we're surely going to see it again. But if it's a bad gradient, we want to limit its impact. The problem is that it's very sensitive to this parameter right here. And the reason is it's not adaptive. So what do they mean by adaptive? What they do is the following. It's almost the same. So as you can see, G is the gradient. So this part right here is the same. You want to scale the gradient, but you want to not only clip the gradient to its own norm, but you want to clip the gradient to the ratio, to this ratio right here. So the ratio is going to be how large the gradient is versus how large the weight that the gradient acts upon is. So if you have a small weight, if you have a small weight and you suggest a small change to it, fine. But if you suggest a big change to the weight, then it's like, I'd rather, sorry, I probably should draw this like this. So small change, fine. Large change, not so fine. However, if you already start with a large weight, then, large changes might be appropriate because that's the general scale of that weight. It is an approximation, right? It is not the end all. It's simply a good heuristic, because you can make cases where just comparing these norms don't mean everything. So if your weight is this and you have kind of a gradient that's really large that goes into this direction, that might be bad because you kind of scale the gradient by a factor of 3 right here. But if I take the same length gradient and just put it into the other direction, you've not scaled the weight at all, basically, but it's the same length of gradient. So just looking at norms isn't everything, but it seems to be a good heuristic. And with that heuristic, a lot of the problems of batch norms fall away. So they do ablations right here, where you can see that, for example, if you compare batch norm networks, the normalizer-free resnets from the last paper and the normalizer-free resnet plus this adaptive gradient clipping, you can see that after a certain batch size, the non-AGC network simply collapses while the batch norm one and the gradient clipping one prevail. So this seems to be the recipe to go to higher batch sizes. Pretty cool. But over here you can see, here is a different thing. Here it's top 1 accuracy versus clipping threshold. So where do you set, of course there is still this parameter here. And they complain that it's very finicky with if you don't do adaptive gradient clipping. So I expect this to not be as crucial if you do non-adaptive gradient clipping. However, here you can see that it has a crucial dependence on the batch size of all things. So you can see at small batch sizes, you can get away with clipping at a pretty large threshold. But then at large batch sizes, you can see you have to keep the threshold pretty low, because if you clip it higher, then it collapses. Now, I was told that one of the problems with batch norm is this dependence of training data points to each other. And I kind of expected this paper to fix it, but it doesn't in a very subtle way. So here is how the gradient clipping works. I told you right here, if the gradient's too large, we're going to clip it, right? Pretty simple. If it's too large, just clip it down. But what is a gradient? A gradient is actually composed of the batch of data that you feed through, right? So you feed a batch of data through a network, and then you have a weight somewhere here, and the gradient that you get for the weight, so maybe the weight is here in weight space, the gradient you get for the weight is a sum. So your gradient for your weight of f of x is going to be, so this is a large X, this is all the data, is going to be a sum over your data points of the gradient, with respect to that, because your loss, this is a loss function, that your loss is a sum, so your gradient is the gradient of a sum of loss functions, and these are interchangeable. Don't come at me, math people, not always, but in this case, I guess. So I hope you can sort of see that your gradient is going to be a sum over data points, or a mean over data points. And that means that it's not actually one gradient. This one gradient is made up by many, many data points pulling that weight in different directions. And the gradient you end up with is simply the average over, or the sum over all these gradients that the individual weights put it. So if you now think this in terms of gradient clipping, and you think that during the data feeding process, during the training process, every data point is an sort of an estimate of the whole data set, that means that your gradient is going to be noisy. That's the point of SGD. What happens to noise if you average it over a bunch of IID samples? It gets smaller in relation to the signal, right? If you input the whole data set, you have no noise. You have a perfect gradient, at least over your training data. As you make the batch smaller and smaller, you have more noise. So if you clip on the final gradient as opposed to the individual data points, and I've checked in the code, they first do the sum or the average, then they do the clipping. If you do that, that means now the effect of the clipping is going to be dependent on the batch size, and it means that you implicitly interconnect your training data, because if you have a noisy process, right? So if this is your base noisy process, and you always sample two things from the noisy process, it has this much noise, you're going to get something that has less noise because it's the average of two things. Now, if you average over 1,000 samples, you're going to get something that has very little noise, right? Every now and then it has a bit of noise. Okay. What you want to do with the gradient clipping is you want to limit the impact of bad training data points. Training data points that just tell you to go a lot into a bad direction. What does that mean? If I have one bad training data point in my batch of 4, that is going to spike the gradient a lot, like right here. So my gradient clipping can be pretty high if I want to limit the impact of that bad data point. If I have a bad data point, my gradient is going to spike pretty heavily, and therefore my clipping threshold should be high. However, if I have one bad training data point in 1,024, it's only going to spike the total gradient a little bit. And therefore, in order to filter out my bad training data points, I need that threshold at a much lower level, right? And therefore, I'm going to, filter out that one here. Now, so that's what I mean. It makes the training data points implicitly dependent on the others in the batch, as batch norm does. It just doesn't do it explicitly. But still, there is a dependence on the batch, which I guess you could solve by doing the clipping before you do the averaging, but it's not as easily implemented in the frameworks that we have. By the way, if you do, and if that gets you a better network, cite the channel. On the way to become the first cited YouTube channel in a machine learning research paper. I could be wrong though. I mean, I've looked at the code. It could be that they do it before. I don't know. Okay, so that's the deal with clipping and my issues with the fact that this does still depend on the batch. So we haven't actually solved the dependence on the batch yet. We have probably solved the computational issue. They say, for calculating batch norm, it takes a while and it takes lots of compute. This here, it still needs compute. However, probably not that much, since you can just do it during the backward phase, right? You don't need anything during the forward phase for doing this clipping. You simply, during the backward phase, you need to normalize, clip, and you're good. So we can take that one. And then my third criticism right here is that they say the second criticism on batch norm is that it has different train time behavior as test time behavior, which we discussed, which is true. But then what does their network contain? Dropout. What's the property of dropout? It has a different behavior at train and at test time. It's okay. We get that batch norm has these limitations, but your paper doesn't necessarily make them better. It just kind of shifts them to different things. Okay, enough rant. So the second part of the paper goes into architecture building. So I actually don't want to touch this as much, but what they do is they say, well, now we go about building a beast architecture that just outperforms everything else. And I'm not sure what it has to do with normalizer-free networks. Like, this is something you can do with or without batch norm, but they come up with this new architecture right here, this new block. Let me scroll to the end. These new 2 blocks for ResNets. So the right one is where you do not have a kind of a down or up sampling, and this one is where you do. But they have done a lot of search, and you can see here are the beta and alpha parameters to make this normalizer free. But doing architecture search, you can do that by yourself. Like, you don't need maybe you need the normalizer free, but they don't make it clear that these two things are so intimately connected. And then they get the model they get up here. And there is quite a bit of evidence in the paper that, there's quite a bit of evidence in the paper that this adaptive gradient clipping actually has some nice properties. Yeah, it allows you to go larger batch size and so on. But again, it's a bit unclear what gains come from the normalizer free, what gains come from the adaptive gradient clipping, and what gains simply come from the fact that they have better architectures. So their whole point in architecture search is that efficiency net, what it tries to do is it tries to achieve an accuracy with as little flops as possible. However, modern accelerators cannot necessarily make use of those, savings in flops because, they have certain constraints. And therefore, this network right here, it focuses explicitly on training latency, which means that if you use current hardware, which means GPUs or TPUs, how fast is training? So for a given time of training, how much accuracy do you get? And there, since it's particularly built for that, as you can see, it beats EfficientNet by a lot. However, if you look at this in terms of flops, they have a graphic down here. So if you look at this in terms of flops versus accuracy, as you can see, it aligns with EfficientNet. So the kind of line here is pretty, as you can see, like it's pretty straight. It's as if you were to scale up the EfficientNet architecture for a bit more in terms of flops. So this is better in terms of, so this is more optimized for current hardware, this kind of networks. Yeah, so that is pretty much it. They do a lot of ablations, comparisons, and it's not like I don't believe that the adaptive gradient clipping is, does nothing, or that, clearly they always do experiments. They compare the normalizer-free ResNets with the batch norm ResNet, so they try to isolate the individual parts. Still, I'm not sure how I feel about papers that have, a lot of different things in one paper, and then they get state of the art. You never exactly know why that is. And the last thing I want to mention that's cool about this paper is Appendix E. Appendix E, I'll show you that. Appendix E is negative results, and this is really cool. So here is a list of all the stuff they tried that didn't work. And, it's one page, but still, it is very, very good, even if it's only to see that other researchers try a whole lot of stuff and fail as well. So I invite you to check out the paper. I've linked the code. You can take the code. It's in JAX, which is pretty cool by itself. And with that, that was it for me. Bye-bye.